Hi everyone, thank you so much for taking the time to come for our SVD. It means a lot to us. We're Team E, ParaDocs, and our team comprises of Paramji, Live, Abhishek, Kimi, and I'm Shivangi. We're also mentored by Dr. Branko, Parker, Sundaram, and Kaushik, and we truly appreciate that Parker and Sundaram took the time to be here with us in present. So let's dive into what our project is about. Osteoarthritis is a medical condition in which the cartilage at the ends of our bones start to wear and tear, causing the tibia and femur to rub against each other. In case of severe pain, doctors prescribe getting a total knee arthroplasty done, which means the knee is replaced. In fact, in the United States alone, 790,000 total knee replacements are performed annually. How the surgery happens is that, so we have a model over here. There are 5 planar cuts that are made in the femur and 1 planar cut in the tibia, and an artificial patella is attached to the ends, and the total knee replacement is done. Now, how these cuts are actually made is that in a robotic surgery, you're going to have a surgical guide placed on top of the femur, and that surgical guide has slots which guide the surgeon about where you actually have to make the cuts. To place this surgical guide, there are 2 pins that are drilled parallelly into the femur, and along these pins, the surgical guide is slid down. So once this procedure is done, it's going to look something like this on an actual knee, where you have the 2 surgical pins over here, and the surgical guide has been slid down. The retractors are to move the skin away. Now, this is a bit out of the scope for our project. What we're tackling to do is part A, B, and C, where we're going to drill holes and place a surgical pin. Not 2 parallel ones, just a single hole and a surgical pin will be placed into it. That's why we're not replacing surgeons. We're assisting them with the part of the total knee arthroplasty, and we will be including their input, and they are going to be continuing the surgery after a part of it has been performed. Our solution is autonomous, non-invasive, and robust. But what do these terms mean? We're an autonomous solution because the trajectory is planned autonomously, as well as the drill is turned on autonomously without any requirement of the surgeon to intervene. But we can take their input to make sure that the registration and the plan that has been done is correct and not causing any harm to the knee. Next, we're non-invasive. So the way robotic surgery currently happens is that these really bulky and invasive IR trackers are hammered into the femur and tibia. We've seen a video of this surgery and it's horrifying. So what we're trying to do is replace this with a non-invasive solution that does not require any of these IR trackers for registration or tracking. We're going to have a simple RGB camera solution, and that's going to try. And we're going to try to achieve the same accuracy that the IR trackers do. We're also a robust solution because we're going to be repeatable, generalizable, non-obstructive to the way surgery currently happens, and not add much of a time overload to the surgical process. So our setup is as follows. As you can see here, we have 3 major components to our setup. First, we have a 7-degree of freedom KUKA LBR Med 7, which is designed for medical purposes. Then we have an Intel RealSense D405, which has been mounted on the end effector over there. And last, we have the actual drill setup, which is of a Dremel 9100. The motor mount has been placed away from the manipulator to make it lightweight. The spindle is attached to the end of the manipulator, and the foot pedal that you see there has been replaced by our own electronic setup so that can be programmatically interfaced.
Hey everyone, I'll now give a brief overview of the process and what we're about to demonstrate. First comes the plan. By this, we don't mean the motion plan, we mean the surgical plan. That is, where do we have to drill? We have a 3D scan of the femur, and the point is defined with respect to it. So the idea is that if you localize this in terms of the whole scene, you now know where to drill. This is done by our registration pipeline, which tries to answer the question, where is the femur here? But wait a second. This is a 3D scan that we obtained by using hundreds of images from an iPhone. This is not what we actually have. The real question is, where is the femur here? This is the noise pointer that we get. And you can also see the output in Arbis of what it looks like. So a registration pipeline performs certain algorithms, applies certain algorithms like clustering, segmentation, and ICP, etc., to localize the femur. And if you know that, we know where to go. And then we can simply go and build that. But before we start the demo, one important question. How would you even know? How would you even know if you did a good job? Because we can drill at any arbitrary point here in KMK. That's done. So to assist with that, we have 3D printed a shell or a stencil where the hole is already marked. So the idea is that after we finish the drilling operation, we'll place it, we can mark it and measure the error. So with that, let's start the demo. Also, one more thing, our accuracy needs to be within 8 mm. On to Paramjeet, will now guide us.
Okay, so coming to the demo, as Abhishek said, we have the bone scan and the point that we need to drill with regards to the scan stored in the PC. So our first step will be registering that scan to the actual bone. So I run this node to we'll see an output of that in Argus. So we'll give it a couple of seconds to look for the femur and line. Okay. So now we can sort of zoom in and see what the plan is. We give this option to a physician as well because we want it to be perfect. So now that we like the scan, I would say go ahead and allow the planner to plan. And since we like the plan, we can go ahead, guys, and do stuff. Do you like the stuff? Do you want to do stuff? Okay. Now we're gonna pause it down. Now that's at a safe distance, let's move it a little behind, away from the board that check out the accuracy.
Sure. This is central, as we mentioned earlier.
John, okay, so we have the stencil that we will keep to the access one, and then on the point. Yeah. It's the whole version. Yeah.
So the whole
We overperformed a little bit. Our plan was to be within 8 millimeters. Yeah.
It's within 2 millimeters. Yeah, it's extremely accurate.
Okay.
Yeah.
All right. Yeah. So we'll do a repeatability check. Let's just run the same process again. There's no way to complicated. There's a whole lot.
Okay, sure. No worries.
Okay, let's do a repeatability check, which let's leave everything the same. Run it again. We have the forms.
So we currently got an accuracy of 2 millimeters, which is well within our accuracy of 8 millimeters. We're trying to see how well we can repeat that accuracy.
Okay, so the same process again. Pre-registered. Pre-registered perception. We'll see the output and yeah. Hold on. Okay, don't change anything, but
You're re-imaging each time, right?
yes, that's a new. And yeah, now I have.
We could also do a thing where in an actual operation, we can use the previous result as the initial transform for the next one, but we do it from scratch to that, essentially. Also, this is the surgical guidance that it was shared.
Oh,
So,
we
we
can
thought of-
just slide that in right now.
We used to talk about this.
Sure.
Should we slide it in now though, because if it drills nearby the whole night?
Yeah, so
Oh, yeah, exactly.
Let's slide it.
Because you have 3 spots, right? You
Correct.
have 3 locations. You can- it just, straight up.
Which is that?
That's the solution, right?
So that's actually this part is the pin holder for the drill machine.
Yeah.
So this is the pin that
The
actually.
pin is also.
So you have 2 of these pins parallel to each other that hold the guide.
Yep.
Yes. Okay. Okay. Okay, we got it under the map activity register.
He gets asked it.
So in this particular run, we
Reload.
are safe to see how repeatable it is and see if
Ah.
we're able to probably do it exactly right there.
So the next time after this, we'll move a bit.
Yeah.
You're going to move it, or are you going to let me?
I'll do it. So that's the problem. If the base is jealous.
Yes, sorry.
Yeah.
So timer takes 10 seconds, we don't allow to start. There's a 10-second delay before actually executing.
So we like plan restart everyone.
Yeah.
Then
Within 8 hours.
well, it is right next to you.
Yeah, yeah. Obviously.
Sentiment.
Yeah. Yep.
Yes.
And you're back home.
So our second goal was built not exactly like that, but just a little bit away, make the accuracy to be about 4 millimeters.
We can.
We can measure with the vertical.
I think the hole is over.
So there's kind of no place for you to mark.
It's okay.
You can just measure with respect to your earlier mark, right?
Yeah, we can do that.
Yeah.
That's about 3 millimeters off glass.
Yeah.
Yeah.
Okay.
Okay, so I think we could move, we don't need to do it a third time, we're going to spec, it's up to you guys. If you want to.
Yeah, but we'd like to demonstrate.
We,
That's fine.
if you want to, like,
Yeah.
we can move it and just show it again, that it will just.
Yeah, we have time, we have 15 minutes, so if you want to do it a third time,
Yeah.
then we can, oh, okay,
Oh, yeah.
that's fine.
Yeah.
What do you want?
No, I thought you were saying you wanted to do it a third time.
No, not in the same position. No, no, no.
So the third time was effectively moving into a different position. So it's a little close. It's a little close.
Yeah, I mean, we can actually spend it. Yeah.
You want to make it more difficult?
SV, let's not. Same process again, we register. Using your spot. I not like it.
So we did the registration and we're not particularly happy with the alignment. It's not exactly perfect and we want to make it perfect because this is a pretty dangerous surgery. So
And since we wanted.
the
to-
surgeon got the option to re-register and now it is aligned better.
So now there's. Plan. While it does that, we're open to questions first.
We can just end the demo and.
Yeah. Okay, you like the plan, these steps?
Yeah. Any briefs now?
Yeah. Did they hit an awkward spot?
No. Actually, I think it's with the
More of a connection issue.
So.
Can you explain that?
So the connection between the robot and the computer needs to be very high quality. So once it drops below, so it actually has excellent signal quality and good quality. But if it stays in good quality for too long, it will think that this is not safe, and so it will stop itself.
Okay.
So we can redo the entire connection again and
And we
redo the
can,
demo.
we can move on to the presentation.
Okay, yes, meanwhile, I'll just move on to our offline results.
So in case I wasn't clear, the connection between the robot and the PC was lost. So we're just redoing the connection because it's a medical robot and it needs to have excellent connection at all times. It moved to a good connection for a little bit of time, and because of that it stopped movement. So I turned off the film for now. We're going to restart the demo, but we can move on.
So these are some of our offline results where we did around, for example, 2 days ago, we did 10 trials. What we noticed was that we were exactly getting an 8 mm error in each trial, which brought our average to 7.5 mm and median to 8 mm, and occasionally going out of bounds. But we noticed that it was always going to a specific spot with respect to the actual plan. So we then realized it's probably a calibration error. So once we added a correction term, these are our average results where we average around 3.9 to 4 mm in general. We make a lot of trials to make registration work. So it's sort of a trade-off between generalizability and accuracy. So one of the biggest assumptions we make is that the femur is always on the left. So if you were to flip it around, it will not work, because this is one of the initial transformations we give to the ICP algorithm. Orientation less than 45 degrees. It's an arbitrary number, but what it means is that you can't twist it around too much like this, essentially. And locate within the crop region. As I showed in the demo earlier, the pointer is very noisy. We do an initial manual crop. So if the bone is obviously not within that region, we cannot do that. And challenges and where we fail in general. Firstly, registration doesn't work 100% of the time in the alignment. It works as in, but the alignment isn't perfect. It isn't real time, as you just saw, and it takes a while. The planner can be slow and unreliable at times. And we don't have obstacle avoidance, and it's an open loop, no closed loop feedback. Our camera calibration can be a bit off at times. Let's not talk about our code base, but that's where we are at right now. And our current mitigation strategy is liberal use of the emergency. So, but as we work towards the FPD, we'll work on removing some of these errors in our system. So coming to the primary difference between our SVD and the FPD. So today we demonstrated a single hole only on the femur with a single camera at the end effector, and everything is static. So for our FPD, we need to drill 5 holes so that the surgical guides can go on. We'll be drilling on both the bones, femur and the tibia. We'll have 2 cameras so that we can see the entire scene and do dynamic obstacle avoidance if we need. And we'll have a proper surgeon arrow instead of having to operate with them. So yeah, that's been our presentation. Thank you, and recollect. Yeah, we can just do that.
Why the questions are happening?
Yeah,
Okay, that's fine. One question, it doesn't really have to do with what you guys have done, but I was just wondering, you talked about the fact that the surgeon can oversee, look at the respiration, see if it's good or whatever. Is the ultimate use going to be such, like, would it be useful for the surgeon to be able to make small adjustments? Or might it be actually worse than that? Or is it better just to say, look, this is not good enough, try it again and hit a button that says, okay, have it do it again automatically? What's the better use case?
So you're asking between that and allowing the surgeon to add offsets?
Well, offsets, yeah, both rotational. I'm thinking, if he looks at it and sees it's not adjusted well, I'm not claiming, I don't know if the surgeon can actually improve that.
Right, makes sense.
So what do you think is going to operation?
Yes, so I don't think that's something we consider because of the way the provision is defined by our sponsor was to make it an autonomous system and not actually take any input from the source if we require. So I don't think we have ever thought of whether that would be more beneficial or less. But
Okay, but it sounds like what I want to describe, you are thinking about some oversight allowed, so certain say, well, that's not good enough, try it again from the start.
yeah, correct.
Yeah, but those are basically we added so that because our estimation isn't perfect. The idea is that once we get to a certain level, we can have good confidence in system and it is.
Awesome. Okay, yeah, a few questions. The first one is, so the point where you want to drill, is it typically on either one like the same or the points?
The points are usually well defined,
Well defined.
but they're specific points because the guy needs to go in a specific place, right, each time. So it'll be like say 2.0 or 2.0. That's all.
Will the surgeon kind of define those points?
You will define the points pre-surgery. Like this is ever before you even enter the operation.
So when you even see, when the system sees the image,
Yeah.
you know, the femur and the tibia, right? They will see also, they will be kind of annotated of where the surgeon wants to drill.
Yeah, it will be annotated not on the actual scene, but with respect to a scan that we'll have of the.
So there would be,
Okay.
yeah, like an STL where the surgeon can place the points that would be required to guide, to place the surgical pins into the guide in. And that would be mapped. Oh, yes, we can do one more demo.
Yeah.
Do the random pose again.
Like the arm follow the different transaction.
But it's farther, so.
Yeah.
What's the best way to place together?
Besides the fact that you can't turn it 180 degrees, that we talked about before, are there any known failure you can experience? No one's. Well, for example, if you don't allow, say, the insertion of the statement that it isn't a good enough registration, you could have a failure of registration.
Yeah. I think the biggest issue we have is that if the pointer is occluded, it's not visible, it doesn't register. In our current pipeline, one of our biggest weaknesses is that our final extracted pointer is this entire region. And the tibia sometimes mess up the registration. So what we're working on is an advanced pipeline where we just remove the tibia entirely, we don't do registration.
Now, given the setup you're putting together, I was thinking, does it make sense? So this is obviously a big change. Does it make sense also to propose that the patient is set up, if let's say this is a system of the future, right? You're removing all the other stuff. Does it make sense, for example, to put the patient in a certain way and add another tool where the leg will go in a certain the way you have it? And then drill. I'm not sure if Smith and Neck or Smith and Neck is really probably the doctors, but I'm just wondering, like, it's interesting how you set it up. You saw kind of a static case.
Actually, the setup we replicated of what we saw in the Cincinnati office. The idea is that knee will be in flexion. So, which is why we try to demonstrate here.
Yeah.
But the real concern in an actual surgery was that you wouldn't get this much of a visibility.
Yeah.
Because the skin will be opened up and you only see like maybe this much.
This much.
Yes, the hard part then is to register with just that.
And the other constraint with the surgery is that, right now it's fairly rigid, that we have defined that the bone isn't moving.
Yeah.
There is motion in this direction. Yeah, there's motion in this direction.
But
So
does it have to be? Do the doctors want that motion?
basically, during a surgery, you have the patient, so this is the hip joint, and that part, the ankle is in a locked shoe. Which is
Yeah.
unlike- So it's constrained there and there.
Like this.
Yeah.
That's leave-
But this in the middle, it's.
Yeah, this is how. it
So
can-
that's generally
Yeah.
held by the physician during a procedure, actual procedure as well. And that will still have some issues. So which is where we'll look at the dynamic compensation.
That is one of the core requirements.
Core requirements.
That's for-
Okay, that's, I think it's worth some thinking and discussing. The surgeons, I don't know, for this, maybe there's something additional. I guess the other thing in terms of the kind of the viewing, the area, are you considering something in addition to the camera you have now, or another location, something higher up? or something else?
Second camera?
Yeah,
Yeah, so in our fall, we're gonna have a second interview with the guy that's gonna be mounted over here on a bench.
in order to see.
Yes, we should give a more holistic view of the entire place so that any dynamic obstacle, any dynamic compensation, anything should be captured by that. And this will be giving a more accurate place of where we're drilling. So
Yeah.
they will
You
be.
still use this for illustration, but that will be to see the entire scene.
To see the entire, okay,
Yeah.
Because you wanna have additional safety, like, okay,
exactly,
something comes from it.
Yes.
exactly. Are the surgeons amenable or open to this? Have you
So-
talked, or you
The
guys?
current system that they have, the coding, is they have a IR sensor far away, so they have to be clear the entire.
Clear the
field of
whole
view.
area, yeah.
So it's already used there.
Which is why our primary use case was to move the camera up on the arm, so that we don't need to block an entire space.
Mhm.
And which is also why we felt the other camera, if it's at a height, then we're not blocking anyone, so.
Yeah.
That's why we're going mounted here, not, about 2 meters away.
Yeah. Yeah. I'm just wondering, I mean, I'm just thinking this is something for conversation, right? If you create a new work area, and maybe even how you constrain the pace, it's something, if it is acceptable, or not, it's acceptable, the surgeon.
I see.
Just simplify, take a lot of the dynamics out. And then they bring in, they set it up, it's of interest to Smith and Nephew also. Also,
So what's your current thought on that compensation? So that registration takes a little bit while as we go. So what are your needs on how to be able to dynamically compensate for that medial lateral motion?
First option would of course be active registration. The alternate approach is that we define tracking key points on the board, and then we just track that at a higher frame rate, because then we know there's relative motion, and if there's motion, then we can rerun registration if it is fast enough. But of course, the first goal is to make it fast.
Are we going to change your fraud requirements for the tolerance, error tolerance? Right now it's 8 mm. What is it?
I think it's all of that.
Is it going to change to something smaller?
Oh, yeah.
Yeah, we're gonna make it more accurate.
So I think the initial overall goal that Branko gave us was, I think, 2 mm 2 degrees. So right now we're not looking to rate this.
We're gonna have an orientation error as well and a 2 millimeter position error.
So that's our
So
FP.
How did the third hole in the
Just have
Just slightly below, same error, but in the other Yeah. it was-
So the dynamic is essentially the idea is that somebody will be moving, and then the end effector will try to track it basically and account for that.
Yeah.
But what happens like it's like the drill is ready to go in. Like last second, and then this loops like.
Yes, that exactly. There are two, if it is a small error that can be compensated with a trajectory change, we do that.
Okay, good.
If it is too much, it is immediately
Can you
seen.
do the same thing? Okay.
Then we change the look.
Okay, you can find it out later on.
Your registration process.
Yes, yeah, exactly. Or maybe the surgeon will call because you're saying, you said you're not replacing it.
Yeah.
Yes.
Yeah.
So the surgeon is allowed to go there and just hold the case at the last second.
Yeah, maybe we can try that out.
No, I'm serious. I mean, it's like,
Oh,
is it something you put on this to limit the motion? That's why I was saying block even instead of blocking here, maybe blocking this.
I don't
But
think
ideally, we want to seamlessly integrate into the.
Understood.
there is a lot of retractors and everything in place, so I don't think anything can be held right near the patella, only towards the end you can clamp it down.
Yeah,
I
so
don't-
maybe the surgeon, whatever.
Yeah,
You try your dynamic as best as you can.
otherwise you didn't begin and hold.
Yeah, exactly. That's the point. Yeah, okay, great.
Thank you
very
so
much.
much.